Hello everyone. In this video, we shall be discussing the velocity potential function in detail. This is an important concept in fluid mechanics, specifically in fluid kinematics. We will understand what velocity potential is, its physical meaning, and how it relates to fluid motion. We will also see how fluid particles move based on this concept and derive the governing equation. Finally, we will look at practical applications to understand its significance in real-world flows. Imagine you have a perfectly smooth landscape, like a gentle hilly terrain. This surface has different features such as slopes, valleys, and flat regions. Now observe the image carefully. You can see a slope on the left, a valley in the middle, and a relatively flat area on the right. Now I place a small ball on this surface. At this moment, we are not analyzing motion yet. We are only trying to understand the surface itself. Think of this surface as representing a quantity that varies from point to point. At different locations, the value is high top of slope, low valley, or constant flat region. So we now have a surface where a property varies smoothly in space and a particle placed on it. Now let us observe what happens to this ball. If the ground is perfectly flat, there is no slope. So the ball stays exactly where it is, there is no movement. If the ground is sloped, the ball immediately starts rolling downhill. This happens because there is a change in height. Now observe carefully. At any given point, there are many possible directions. But the ball does not choose randomly. It always moves in the direction where the slope is steepest. If the slope is steep, the ball moves faster. If the slope is gentle, the ball moves slower. So two important observations. The ball moves only when there is a slope. The speed of the ball depends on how steep that slope is. Now observe this carefully. You do not need to tell the ball where to go or how fast to move. The shape of the surface itself completely controls the motion of the ball. The ball is placed at a higher point. At that location there is a slope. Because of this slope, the ball naturally starts rolling downhill. No external instruction is needed. At every point along the path, the ball simply responds to the local slope beneath it. If the slope is steep, it moves faster. If the slope reduces, it slows down. When the ball reaches a flat area, there is no slope. So the motion stops. The motion of the ball is completely determined by the shape of the surface. The ball is not deciding anything. It is simply reacting to the slope at each point. So the ball is just passively responding to the local slope under it. In fluid kinematics, we define a quantity called the velocity potential function, denoted by letter 3d5 phi. Think of this velocity potential as an imaginary or invisible surface that exists throughout the flow field. Each fluid particle behaves like the small ball on this surface. The motion of the particle is governed entirely by the shape of this potential surface. If the surface is steep, the particle moves faster. If the surface is gentle, the particle moves slower. Therefore, fluid motion is not arbitrary. It is completely dictated by how the velocity potential varies in space. So, the velocity potential letter 3d5 can be understood as an invisible landscape, and fluid particles move exactly according to its local shape. Fluid particle motion can be understood as motion over an invisible surface. A fluid particle does not decide its path, it moves only according to the shape of the velocity potential surface at its location. If the surface is flat at a point, the slope is zero. Therefore, the velocity is zero. If the surface has a gentle slope, the particle moves slowly. If the surface has a steep slope, the particle moves faster. The direction of motion is always along the steepest slope of the surface. Hence, both the magnitude and direction of velocity are completely determined by the local shape of the velocity potential function. This analogy is valid only for irrotational flow. In irrotational flow, fluid particles do not spin about their own axis. They only move along the slope of the velocity potential surface. So just like a ball rolling down a hill, the motion is completely determined by the surface shape. Now consider rotational flow. Here, fluid particles have rotation or spin. This motion cannot be explained only by a surface slope. A ball on a curved bowl may start spinning in circles. This behavior cannot be described as simple rolling down. Therefore, velocity potential exists only when the flow is irrotational. If rotation is present, this analogy breaks down. Imagine an invisible, perfectly smooth surface spread across the entire fluid domain. Every fluid particle behaves like a small ball resting on this surface. The particle does not choose its path; its motion is completely governed by the local slope at its position. If the surface is steep, it moves faster; if the surface is flat, it comes to rest. Thus, the particle continuously moves along the direction of steepest descent. This invisible surface is called the velocity potential, denoted by phi. If the invisible surface is flat at a point, the fluid particle has zero velocity. If the surface is gently sloping, the particle moves slowly. If the surface is steeply sloped, the particle moves quickly. The direction of motion is always along the steepest downward slope. Thus, the slope of the velocity potential, phi, determines the velocity. A small slope gives small velocity, a moderate slope gives moderate velocity, a large slope gives high velocity. In general, the fluid moves from higher potential to lower potential. The steeper the decrease in phi, the greater the speed. Velocity potential phi is a scalar field, like an invisible surface in space. A fluid particle behaves like a ball placed on this surface. Its motion depends only on the local slope. If the surface is flat, velocity is zero. If the slope is gentle, motion is slow. If the slope is steep, motion is fast. The direction of motion is always along the steepest downward slope. Therefore, flow always occurs from higher phi to lower phi. Mathematically, velocity components are given by u equals minus d phi by dx, v equals minus d phi by dy, w equals minus d phi by dz. Thus, velocity is the rate of decrease of phi in space. Consider a steady, incompressible, irrotational, two-dimensional flow. Start with the continuity equation. Partial u by partial x plus partial v by partial y plus partial w by partial z equals 0. For two-dimensional flow, w equals 0, so partial w by partial z equals 0. Therefore, partial u by partial x plus partial v by partial y equals 0. Now define velocity, using velocity potential phi. U equals minus partial phi by partial x, v equals minus partial phi by partial y. Substitute into the continuity equation. Partial by partial x of minus partial phi by partial x plus partial by partial y of minus partial phi by partial y equals 0. Differentiate. Minus second partial phi by partial x squared minus second partial phi by partial y squared equals 0. Factor out the negative sign. Minus of second partial phi by partial x squared plus second partial phi by partial y squared equals 0. So, second partial phi by partial x squared plus second partial phi by partial y squared equals 0. This is the Laplace equation for velocity potential in two dimensions. Physically, this means there are no sources or sinks in the flow and no accumulation of fluid. In three dimensions, second partial phi by partial x squared plus second partial phi by partial y squared plus second partial phi by partial z squared equals 0. Hence, velocity potential in incompressible, irrotational, steady flow satisfies the Laplace equation. Velocity potential is widely used to analyze real fluid flows. In ocean currents, it helps describe large-scale water movement. In atmospheric pressure systems, it explains flow from high-pressure regions to low-pressure regions. In climate and jet streams, it helps model high-speed airflow patterns. In underground water flow, it is used to study seepage and groundwater movement. The same concept applies to planetary atmospheres such as Jupiter and wind patterns on Mars. It is also useful in studying atmospheric flows on exoplanets. In coastal regions, it helps analyze phenomena like upwelling. Thus, velocity potential provides a simplified and powerful way to understand and predict fluid motion across different natural systems. Thank you so much for listening to this video. I hope you have understood the concept of velocity potential function. Consider subscribing to my YouTube channel for more such videos.